and I did the falling slinky. So introduction. So the purposes of this lab are to observe an object's projectile motion when it has like tension force. Also to compare the differences between this projectile motion and to a computationally based model, and also like the tracked experimental data. The main result is that through this experiment, we correctly computed the expected Y position of a drop slinky using our code models with a little bit of error. So some physics ideas and equations. So the basis of this is Newton's second law. So we use this to derive velocity and displacement update formulas, and we use it for like momentum and stuff like that. Velocity and displacement, you can see the formulas here. It's effectively just going to be VI plus F net over M times delta T for velocity, and then RI plus V average times delta T, which is going to be around VF because of, so drag formula, we said it was going to be negative B times V squared times V hat. So that's going to be negative drag coefficient times the speed of the object squared times the normal vector, which is like the direction, and then gravitational work, mgh. Assumptions. So our main assumptions for this experiment are that gravity, tension, force, and drag are only forces acting upon the projectile. This is important because if they aren't our only forces, our calculation for our net force would be incorrect. And that also, this is going to assume that the slinky has no force applied to it when the person drops it, i.e. there's no initial velocity, so the initial velocity is 0. Also another assumption is that our tracker data is accurate. The system is going to be the slinky being dropped, and the surroundings is going to be everything else, like the earth and the atmosphere. Here's the tracker video. I'm only going to play some of it because it's kind of too long, but you can see like the slinky is moving, and then you can see here it's stationary at the bottom, and then I also tracked like until when it starts falling. So here are the stats. The most important stat that we see here is this Y versus, or time versus Y graph here is going to be really important. And it's not here, but I'm going to use this data chart for the initial position in the code, like right here, ball.position. position. This is pretty much where it is in frame 0 of the video. The ball.m I said was 0.218 kilograms because I think I just Googled it. B was the drag coefficient, and I said 75, and I got that from testing the code to see which graph most closely represented the tracker data. Here I have F graph being 0, negative mg 0. I'll get back to the tension. So F net, I just said was the sum of all forces, and then ball.velocity position I got from the two graphs, or the two equations I talked about earlier. We know that F net equals 0, or it has to be true because the bottom of the spring wasn't moving, so the sum of all forces has to be 0 for there to be constant velocity of 0. So that means, 0 equals Fg plus F tension, which means F tension must equal negative Fg. And this is the first part of the while loop where the bottom of the slinky isn't moving, and here's the second while loop where the bottom of the slinky is actually moving to the ground. Again, F gravity, ball velocity, and ball position are the same from last slide. F drag is going to be negative B times V squared times V hat, which is effectively what this equation is doing. And then F net is going to be F grab plus F drag, and there's no tension because the slinky is condensed. And F net will not equal 0 here because it's moving, so we don't need to bother with calculating anything else. The code output, this is what the glow script gets. You can see here's the first part of the while loop where there's no movement of the bottom of the spring, or the slinky, sorry. And then here's the actual second while loop where the slinky is moving. Differences and errors, you can see here, the data from file 1 is going to be the real tracker data, and then the blue one and the orange one is going to be the glow script data. And you can see pretty much like the two graphs pretty much intersect, or like they overlap very well, except here at the bottom. And I think that's honestly just like a tracker, my tracker data error rather than computational error, like graph or code error, I guess. So errors, we have probably the incorrect assumption of 3 forces. We're assuming that the only forces are gravity, tension, and drag, but in the real world, there's always going to be more forces. So just assuming these 3 aren't going to be enough. And the tracker frames, because I had to, track over like 100 frames, I think. I'm sure I made some mistakes at some point, and it's going to lead to an incorrect position, which leads to incorrect graphs. So here are the whats. There's only one question for this one in the lab instructions. That's where I got it from. Does the bottom of your model slinky stay stationary just like in the video? Yes, up to a certain point. This point is when the top of the slinky reaches the bottom of the slinky, so when it kind of compresses back to its natural state, then it begins to fall to the ground, which is what we saw in the video, of the tracker video as well. So why is this the case? That's because until it compresses, the tension force of the slinky counteracts the gravitational force that should bring the slinky downward. So like tension force brings it up and then gravity brings it down. And then as it compresses, the tension force decreases, which allows gravity to bring it downwards. And that's log 5.